All right, hello everybody. Hello, hello. You guys realize we have two class periods after today, and then the semester is basically over. So next week is our last full week of classes. That's kind of crazy. It has gone by really quickly. So come on in here. Yes. You know, this semester I thought it was going to be not as bad, but it's been kicking my butt. I'm still behind on grading. I've caught up a little bit. I graded maybe 20 of the exams, and I did the ones that were not through the automated system. So the next step will be processing the automated, and once I get that system running well, that'll kind of speed things up. But so far, not quite done yet. I will say though that I am committing to giving you your grades back for your second exam and your third homework by Tuesday. So that's my commitment. I also am planning to post homework number 4 today. Excuse me. Yeah. Doesn't quite help that I got a dog last week. It's a great dog, very happy, but at 5 a.m. this morning, there's all this thunder and lightning, and the dog was freaking out. We had to wake up and help the dog, let it out and stuff. Okay, so I'm just going to type a message for anybody that arrives late. Exam 2 and homework 3 grades should be posted by Tuesday next week. I'm also going to post homework for today. And then the last announcement here, and let me know if for whoever comes maybe midway through or something, I hope this message history might be helpful for the announcements. So let me know if you do end up finding that. The last thing I will say is I have also been slacking, I guess, or not staying on top of the participation assignments. I do want to give you lots of participation assignments. I think the questions are, kind of interesting in that it adds a little bit more content to the course, making you think about things in different ways. And it's not really hurting you very much if you actually miss the questions. You get most of the credit regardless. So I'm going to post a few more quizzes, give you opportunities to participate in them and improve your grade that way. And if there are any issues with these participation grades, I'm going to be particularly lenient with those because I for one have not been on top of it to give you the experience I wanted to, and it's just difficult with everything being online for you guys. I'm totally aware that tracking all the different assignments is not ideal, and so I'm gonna be lenient in that regard. Maybe keep them open a little longer or something if I need to. Homework 4 will be due a week from today, because that's when we'll have the exam review. And so I want to go over homework 4 with you. It's going to basically be on the activated sludge stuff and the BOD modeling things. So today we should finish all of the relevant content for the homework and really for the final exam. And then on Thursday we'll review all of that. So next Tuesday we're going to do more of a kind of a special topics, either membrane bioreactors or kind of treatment of biosolids produced during wastewater. And so if anybody has any special requests, I can adjust that accordingly. Okay, and then I will also post remaining participation assignments. Probably today. And those will be due, really, I'm kind of flexible on those. I don't want you to be worrying about them during exam week, but so I'm going to put a deadline before final exams, but if something comes up and you didn't get to them and you need to get to them, I probably will be okay extending them. I'm going to give you a deadline so you have the reminder so that you're aware if you missed it. But yeah, be in touch if there's any issues with that. Those don't take me very long to sort the grading through, so that's not going to be a big issue. Okay, with that, I'd like to get a little bit of your feedback, and if you could do me a favor and use a combination of Kahoot, which I'm going to pull up on the screen in a second, and the Twitch chat. Add stuff into the Twitch chat if you need any extra, or maybe have something a little bit different to say than what I'm asking. And actually, one thing I meant to do for this is adjust the time. So I'm going to give you more than 20 seconds for each. So I'm just going to do that real quick. You can see the process here. Just be a moment. Recently, Kahoot changed their way of things, so I have to make it like a quiz, quote unquote. But it's a poll. So there's a right answer, but really there's no wrong answers, right? Okay. So it's going to generate a pin, and then on a phone or on your computer, wherever, whatever you've got, go to kahoot.it, put in that number, sign in with a username. I don't really care so long as you're not being inappropriate with username. Make some puns, be Krabby Patty. Do what you like. So I'm not recording this Kahoot or anything. So just aside from we're recording it obviously for the lecture, but So go ahead and join that. Hopefully we'll get a few more of you. It looks like there's 19 of you viewing right now that I can see on Twitch, excuse me. So I'll wait for a few more of you. Fatberg. And maybe you can type in the chat if you enjoy these. So essentially, the questions I'm going to ask here is really looking for feedback for next year. Next time I teach the class, presumably will be completely online. And so I won't have quite the same environment. I won't have the fish cam. I won't necessarily have all of the amenities I have at my home office here, but I still can record the lectures. And if you ever happen to be looking at my Twitch page, you'll probably see that I do the same for my grad class, but normally I teach that one in person in class, and the video quality is not as great. So anyway, my question for you is, next time I teach the class, I'd like some feedback on how you felt things went this time and how I could best transition into next time. So for anybody joining later, Kahoot, or kind of in the middle, .it, and then the pin here is that. Okay. So let me know what you think. And the first question really is, okay, so next time, what do you think about the balance of example problems solved in class? Should I add more? Was the number good? Add a few more, spend less time on it. Let me know what you think. And I can mute the audio if it's bothering you. So, of course, none of you thought I was wasting any time there, and most of you thought a few more problems would be good, and some of you felt like a lot more problems. Okay, good, thank you. I will say that I think I've made a little bit of progress here. It used to be much more on the lines of needing a lot more problems, so I'm glad that I'm heading in the right direction, I think. And I'm sorry I didn't provide more for you. By the way, it's highlighting this one answer as if it's the right one. Don't just ignore that. That's not, so apparently Brady's the only one that selected that, and I'm sorry for singling you out. didn't mean that. Okay, so next time, what about my presentation style? In the classroom, I can still project the screen and record it for later. And so, do you like the fact that I use the little pen tablet, the drawing pad, and the PowerPoint? Do you have some other comments? Do you feel like I needed to change something? Would really appreciate if you just type in the chat if there's something that you felt ought to be improved, especially if I'm in person at a podium on my laptop and perhaps still doing the live stream and the recording, but just mostly focusing on the in class. Okay. Well, good to know. Thanks for that. And I do apologize that, the writing pad, it might actually be in some sense a little better than my normal way of things, because I can't promise that my handwriting is any better on a piece of paper. That's how I used to do my notes primarily, is have a few PowerPoint slides, but mostly using like a pen and paper drawing pad that's projected. And I think this is an improvement on that, so I'm glad to see most of you liked that. Okay, what about attendance next time? Do you think if I'm doing this kind of hybrid mode, people could watch remotely if they felt like it, because I can live stream or catch up later? Should I require attendance? What do you think? Would that be helpful? Would you learn more? Should I encourage it but not require it? Or just don't even bother? You feel like learning at your own pace is the best. Okay, that's good to know. So probably something like encouraging students, maybe providing some incentive, but not like a forceful type, you fail if you don't attend. Seems like what you guys think would be best. All right. So next time, about the recorded lectures in particular, should I continue to record them and post the notes? Did you like the video but not the slides, or like the slides not the video? Do you feel like in person I don't need to post either? I just wanted to get your opinion on this. I'm betting that I know what most of you will answer. And I would normally post my notes anyway, particularly in case there's anybody that needed a note taker or something. That way there's just a little bit less stress and logistics involved with anybody who needed a note taker. But just to answer how you feel about it, and that's kind of what I'm curious about, is how you're. Okay, good. Yeah, and I thought that was probably probably going to be the response. Good. I'm glad to hear that. I know that this has just been a really strange semester because you didn't even have the option to participate directly in class. And okay, so I think that's it. And let's see who wins. Woot woot. All right. This means nothing. I'm just letting it play. Well, good job, William J. There's a lot of times that's just the first person to respond. I'm glad you like the fish can. I really am. I've mentioned it to a couple people before, and they're like, I feel like I'd just be distracted. And my response to that was like, well, do they really want to be watching me the whole time? Like, maybe I should just do this, Maybe that should be yes. Now I need a dog cam. I would have invited the dog in, and maybe I will next week. But one of the first times we had the dog in here, um, it was still kind of learning the house and things, and then it decided that the books right behind me here were a good place to mark its territory, and that was not quite acceptable, if you know what I mean. So dog is currently banished from this area until we are more confident in his house training. But a dog cam would be nice, and maybe I should find a way to live stream in a fish cam. Maybe if I've got some extra time at the end of class today, I might think I have a short video that I could play of the dog playing in the yard. So we have a little bit of a dog cam. But anyway, yeah. Thank you guys for the feedback. I really do appreciate it, and there's more space in the course evaluation forms to give me more specific feedback in different aspects of the class. Kind of a longer form, fill in the blank. What do you think? Completely anonymous. So I always appreciate that. Especially if it's constructive. Feel free to be critical. It'll go further if you make it constructive in addition to being critical. But if you just need a vent, I'm not going to be mad. Do what you need to do. And I also appreciate compliments and whatnot. So obviously, I'm a human being. If you didn't know. Okay. So anyway, last time we left off, we had discussed BOD downstream, this biological oxygen demand, and we just started to talk about what happens when you discharge wastewater into a river or a stream, and you're looking at what's happening to the oxygen as it's flowing, the oxygen content of the river as it's flowing, through kind of like a plug flow reactor. Water is just heading through, and the amount of oxygen in the water is eventually going to sag. So we have this dissolved oxygen sag curve where at some point we're going to have the lowest amount of oxygen, and that's really going to be pretty much the most important part when we're trying to regulate how much BOD are we allowing into our river. So BOD is not inherently a terrible thing. If you have a large river that's got lots of oxygen in it, you can put in a fair amount of dissolved organics that are biodegradable without much worry of disrupting the system too much. And this happens when it rains. We've got so much rain lately in Baton Rouge that the rivers are swollen, maybe some flooding and stuff, and all this organic matter from the soil and the sediments that are kicked up, that's all going to be contributing to an oxygen demand. And so to an extent, this is a natural occurrence, is BOD added and oxygen sagging because of that. But what we want to make sure is we're protecting the intended uses of the water, right? So if this is sagging all the way down to like 0.5 milligrams per liter, we're going to have big issues because that's not going to support wildlife. But if this is only sagging down to maybe like 6 milligrams per liter, there's probably no problem. I'm betting that some of the natural waterways around here in Louisiana, given the heat, especially in the summer, are much lower than 6 milligrams per liter just where they sit. And that can't support certain types of aquatic life, but a certain areas just specific organisms will adapt to the environment. We just don't want to be causing the disruption ourselves. So we're going to look at this dissolved oxygen, and then we're going to really pay close attention to the deficit. And I'll go ahead and highlight this with a bit of a different color here. So the deficit, OD, is going to be that difference between the oxygen at saturation in the current amount of dissolved oxygen wherever we are. So initially we have a little bit of a deficit here. So this is OD initial, I guess we could say. And then we would have a maximum deficit where the sag is the greatest. So this would be OD max. So be thinking about it in that term. At some time after the discharge or some distance downriver, we have a deficit in the oxygen that is the most severe. And understanding when that's going to happen and how bad it's going to be when it happens is one of our primary goals here. Okay, so when we're thinking about this, one of the tools we can use when investigating this process is to look at the total organic carbon. Now, the TOC is actually very similar to the method that we talked about where we measure the chemical oxygen demand. Because what we're doing is we're taking a sample of water and we're determining how much of that, in that water, if we treat it to a really harsh oxidizing conditions, we're measuring the mass of carbon per volume. So that's total organic carbon in milligrams of carbon per liter. And that's analogous to oxygen, we'll just abbreviate to O2 demand from oxidizing organic stuff. And that's going to be per liter or per volume or whatever. So that's going to be like milligrams of oxygen demanded from that chemical oxidation process. Okay, so I'm just writing this out to show you this technique that we use to define total organic carbon is pretty much the same type of technique we use to get that chemical oxygen demand. We are technically measuring something else. We're measuring the mass of carbon material, like, you could measure the TOC of caffeine in your coffee, or of all the types of organic compounds in your coffee, rather, caffeine being one of them. Or you could measure the oxygen demanded by oxidizing all that stuff. So they're kind of similar. So anyway, we can look at that TOC over time, because TOC is fairly easy to measure. And if we were to look at it in solution, the biological activity will be consuming it. And so we expect that we'll start with a fair amount, and then it'll decrease pretty quickly, and then maybe start to level off. So we can understand how much oxygen demand is going to be exerted based on how much organic carbon is there in the first place. So this is a decent metric, and this TOC this total organic carbon is essentially, most of it is considered a substrate. Most of it is something that bacteria can consume and make and use for food and for energy. There's going to be some fraction perhaps here that really is not very active and not really biodegradable, or not easily biodegraded. So there's probably going to be a portion like that. So when we take a look at the system as a whole, what we're looking for is a way to understand, we know how much substrate we're discharging from our wastewater treatment plant. We know we're adding some organic matter. So we want to connect that concept, and maybe we monitor with TOC, but we want to connect that to the, that BOD, to the river, in order to predict when we have that sag curve, happens at its, when that happens. We want to know that point. And it's going to depend on that BOD 5, or, we should be able to use BOD 5. And it'll also depend on the DO at saturation. It'll depend on the dissolved oxygen in the river itself and in the wastewater itself. So it's going to depend on a lot of factors, and we want a mass balance that tells us something about DO in relationship to the biological oxygen demand. And we're going to do that as if it's a plug flow reactor. Okay, so getting to the math of it, we have a few definitions I want to cover that expand just a little bit further from the DO, or excuse me, from the BOD topics that we were talking about last time. So if we want to know the BOD remaining at some time, we're going to use this term L at time t. So L being the amount remaining. So if we look at L at time 0, then all of it is remaining. Nothing has been degraded yet. So we pour a bunch of biological oxygen demand into a river, and before it goes anywhere, we have that same amount. That's all that we're saying. And one thing we could say is that is the ultimate BOD. So that's the total amount you could ever degrade, is defined as L naught. Then if we're looking at it this way, then we can track how much oxygen demand is remaining, rather than tracking how much has been consumed. And that's just going to be a little bit helpful as we model the system. So we look at how much is remaining as a function of time, and that's going to be a first order decay because the substrate is being consumed by bacteria and stuff. And we're going to have some rate constant. This will be the remaining BOD changing over time. We can integrate that for a batch or for a plug flow system, right? Using theta instead of T. And we get the amount remaining at some time is equal to what we started with times e to the minus k times time. Of course, this k is a BOD reaction rate constant in per day units. And the other important thing here is our initial value for BOD remaining is defined by what the BOD in the river plus the wastewater. So really what we're looking at is a mass balance on a system where we have water flowing down the river and then a discharge of, so an additional stream here, an outfall from a wastewater treatment plant. And then we're looking at right here when they mix, this is our L naught. Okay, that's our ultimate BOD. All of it is remaining. We probably have some BOD from the river itself and from the flow rate there, and BOD from the wastewater. So what we're saying is that L naught, the initial BOD here, the initial amount of BOD that remains, the ultimate BOD, is equal to excuse me, that's not this equation. I'll explain this one in a second. This is saying that Q of the river times L of the river plus Q of the waste times L of the waste is equal to L naught. Okay, so that's just saying divided by Q of the river plus Q of the waste. That's just saying that in why did I divide? That should be multiplied. Sorry, as I mentioned earlier, I haven't had as much sleep as I probably should have got. Okay, so that's what I meant to say. This is a simple mass balance here showing that this L naught can be defined as just what's coming from the stream plus what's coming from the river, right? The waste stream plus the river, and that's the initial amount for the whole flow. So that's just simply a mass balance on the mixture right here. We've done that particular type of problem for a long time. So just keep in mind that that's what we're talking about when we're defining one of these systems. We're starting with where we're at times 0 in the river after they've mixed. Okay, another thing to keep in mind is that the LT is related to the initial amount in a sense that this is like the total, right? The total that we started with equals remaining plus the BOD here, which has already been consumed. Okay, so again, that's a very simple statement to make, but I wanted to make sure that it's clear because that is essentially the definition in the mathematical form, right? The ultimate amount is the amount that's still remaining plus the amount that has already been, the amount of oxygen that has already been demanded. So at some distance or time downstream, we could say LT here and define it that way. All right, and depending on what's going on in your system, it might be, maybe you already have the information about the BOD that has already been demanded at some time, and you know what you started with, and therefore you know the LT. Maybe you have to calculate LT based on how much time it's been. You don't know the BOD that's been demanded yet. Now you have a way, assuming you know this parameter here, the K, the reaction rate constant, you have a way to figure that out. Again, maybe you figure out how much you started with if you know the measurement later, or whatever the case. So we have some tools there that are going to help us understand what's happening to the BOD as we travel downstream. Next, we're going to relate this oxygen demand to the actual oxygen deficit and dissolved oxygen content. Okay, when we think about a river, or even my aquarium over here, the oxygen that is being demanded, I'm gonna make this bigger because why not? The oxygen that's being demanded by the biological stuff. I fed my fish earlier today, and I'm sure he's been excreting some waste. That's gonna demand some oxygen from the water. Now, there's a deoxygenation rate constant because of that. And so that's going to be some rate that we can model. It's going to be a first order rate here. We see it's in per day. So every day, the amount of waste in that aquarium is going to be demanding some amount of oxygen. That's going to be counterbalanced by a rate of re-aeration. So we can say this rate of deoxygenation, RD, and we can set it up and say that's going to be equal to KD, this rate constant, times the ultimate BOD, so the amount of substrate that's in there initially, times e to the minus kd times t. So we have that relationship there. That's the overall rate of deoxygenation. Now, we need to balance that with the rate of re-aeration. So re-aeration is a physical process. That's what the bubbles in the aquarium are there for. That's why it's pushing air through the system. You know, some aquarium filtration systems have a water spillway where it's pumping actually water through, and the water is flowing and making some current in the water, and it's just flowing through. There's a little bit of a filtration thing happening there as well, but mostly it's just that water contacting the air and that turbulence where the water is moving quickly across the surface and contacting open air. That's a physical process promoting more oxygen to be getting into the water. So the current, the water current is important. The amount of motion and turbulence is important. And this physical process, it's like, you know, in a way it's like osmosis, right? There's a gradient. If you have an oxygen deficit at equilibrium, the pressure of the gas phase is essentially going to be pushing gas into the water. And so if you have a deficit, there's a gradient where there's a higher concentration in the atmosphere, and it's sort of pushing in on the water until you reach saturation. This re-aeration is going to be proportional to the deficit. So we have some re-aeration rate constant times the deficit. Now that re-aeration rate constant is also first order. And then we need to define the deficit to know kind of how we're going about this. So the deficit is equal to the dissolved oxygen at saturation minus the dissolved oxygen at whatever time we're looking at. So if you remember, we were looking at that plot where we sketched the DO at saturation. That's maybe 8 or 10 milligrams per liter, somewhere like that. And then our dissolved oxygen sag curve, you know, something like that. And so depending on what time we select here, we see that the deficit is going to be a comparison from here to whatever time we selected. Okay, and we drew this up earlier. I'm just reminding you again here. This is the technical definition of our deficit. It's a little bit counterintuitive to work with deficit because, you know, it's like kind of using double negatives almost. But it's really that deficit that's driving the pressure gradient for oxygen to be added back into the water. So we do have to deal with it in that manner. And likewise, this lets us account for things like the temperature of water is important because more oxygen can go into colder water. Therefore, the deficit is going to be different if the environmental conditions are different. There's some other factors that can play a role too. Okay, so then what is this Kr? How do we know something about that? It turns out that Kr, the rate of re-aeration, is going to depend on the stream or the river conditions. That's what I was talking about with the aquarium, right? The bubbling, the speed, if water is being used to push through it. And you can imagine something like a stagnant bayou is going to be a lot different than Niagara Falls, right? In terms of how much oxygen is getting in. So clearly the speed of the water is going to be important, and the depth of the water is going to be important too. You know, if you consider the Mississippi, that's a lot of water flowing very quickly, but it's also very deep. And so the water towards the bottom is really not going to be in contact with the oxygen at the top. You know, there will be some turbulence that will cause some mixing, but for the most part, there's just not a lot of that water is contacting the surface compared to the actual sheer volume of water that's going through. So we've defined, and this is just something that's been reported, and our book shows us, it's what we call an empirical parameter. So we know that the reaeration rate constant tends to be related to the speed of the river, U, to a 1/2 power, and the depth of the river. And we're using H here to the 3/2 power on the denominator. So 3.9 times the speed of the river, the square root of the speed of the river really, divided by the depth of the river to the 1.5 power. And that's just based on experience, based on studying lots of rivers and how quickly they reaerate. That's just a generic formula that people have come up with that tends to be a pretty good prediction of what happens in a river that's, reasonably river-like, I guess. So this can be different. Maybe this is not perfect, but it's a good approximation, and that's the one we're going to use. So there's not really much rhyme or reason to it, aside from people gathered a lot of data and came up with this relationship that seemed to fit the data pretty well for different rivers, different speeds, heights, and so on. Okay, so as an example, we can take a look at the range of that reaeration rate constant in per day units for 20 degrees Celsius water. And in general, you can look at kind of a small pond, backwaters, it's going to be 0.1 to 0.23. This is why you'll see, especially here in Louisiana, lots of ponds will have a fountain to improve this, to increase it, because stagnant ponds can get pretty stinky if they go anoxic, and that's not going to support any fish. So if you want less stinky and more fish, then you might be looking at adding some sort of fountain to make sure there's plenty of aeration. Sluggish streams and large lakes probably have kind of a slow but reasonable reaeration rate constant, 0.2 to 0.3. And we can just take a look at how this number is changing and increasing. By the time we get to a swift stream, we're looking at 0.7 to 1.1-ish. And rapid and waterfalls are somewhere above that. And these are from studies conducted some time ago. So that's just a kind of an example. And so if we're working with some water body, I'd probably give you one of these, or maybe we'd be looking to solve for it if we had some other information, but just a kind of a scope of what these reaction rate constants look like. Okay, so taking a look at how the deoxygenation and reaeration occurs, we can take a look at this oxygen rate profile. So we have the SAD curve, right? The dissolved oxygen SAD curve, where we start with some and there's some deficit. It gets worse and worse and worse, and then it starts getting better. We're interested in that critical point, but maybe we're also interested in knowing how far until it is restored to a good spot. Well, if we take a look at what's happening to the oxygen, the rate at which oxygen is being removed or added to the system, in comparison with that, what we'll see is that deoxygenation is happening very quickly and at a higher rate than the rate of reaeration initially. That's why this plot is going downwards. Then as we go forward, at some point, these two meet. And when they meet, that is where this plot, we have no decrease or increase. We've reached an asymptote, and it is just simply, it's neither going up nor down. It's going up and down at the same rate, right? That's where these two meet. Where these two are equal is exactly that same point as you see it drawn here. From there, and by the way, this is because that deoxygenation, there's lots of biodegradable organic matter, and so all of that is being eaten and consumed, and it's pulling the oxygen down. There's a high rate of deoxygenation. As we get less and less oxygen, a bigger deficit here, that's pushing the rate of reaeration upwards, and then they meet, and then after that, you see that the reaeration is higher than the deoxygenation. Now, deoxygenation is still occurring. We're still degrading biodegradable stuff. We're still consuming it. We're still demanding oxygen. So for the remainder of this graph, up until there's really no more biodegradable stuff in the river, we are continuing to raise the DO level and decrease the deficit. And that'll just go on for some time. And in practical terms, this is just kind of showing what happens with like a wastewater discharge. But like I said, there's natural processes, natural stuff getting into the water, fish eating organisms and producing waste, and all sorts of stuff being added. So there's all sorts of natural processes that will contribute here, but this is a good depiction of what happens if you do add a specific or a set amount of waste, and watch what that does to the oxygen afterwards. Okay, so then as we're modeling, we take a look at this deficit. And what we want to do is take a look, if we want to look at how the deficit changes over time, we need the two rates. We need the deoxygenation minus the reaeration. Again, this is like a double negative here. We're looking at that deficit changing over time. That means it's going to be the amount we're removing minus the amount we're adding. It's going to give us the net balance for the deficit. And then we've got this equation is what it turns out to be. We're going to skip a few steps here, but essentially, if we integrate that, so this was the deoxygenation, that depends on the amount of BOD there, the amount of time it has been there being consumed, the rate at which that BOD consumption is occurring, the rate of deoxygenation, the rate constant for deoxygenation, all those components together minus the rate of reaeration times the current deficit. Okay, so we integrate that. That is a bit complicated, so we're not going to do that ourselves, and we're just going to let the book do it for us. This is the term that we get, and I'm giving you this term on your equation sheet. I'll do my best. I'll try to post the current equation sheet for you so you can begin studying for the final and use that for your homework, in addition to posting the other materials today. But you'll have this one, and what we see is the deficit is essentially a relationship to these parameters, the starting amount of deficit, or of remaining BOD, so the ultimate BOD, the different parameters, the time at which, the length of time that the water has been flowing downstream, the initial deficit, and yeah, more of these parameters. So it's mostly knowing what these parameters mean and being able to plug in the correct numbers. I'm not asking you to do this integration yourself. One thing that we might notice though is if these rate coefficients happen to be equal here, we end up with a problem because we're dividing by 0. So if we've got that situation where we have division by 0, and only when that happens, only when these two coefficients are the same, this is not when the rates are the same. The rates are a different topic. That's the critical point. But if it happens that the coefficients for reaeration and decay are the same, we have to use a kind of a simplified case, and this is the equation we would use only in that case. So I'm going to give you this one too in case we need it on the exam, but make sure to make a note that you should use this equation unless Kr and Kd are the same, and you've got that division by 0. So only look at the other one if you have the case where you're dividing by 0 and you're like, oh shoot, I can't divide by 0. That doesn't work. Then you need to go to this problem, this equation. Okay, so that gives us the deficit based on some time, right? Now, the real question at the end of the day is, well, when is the deficit max? So when does deficit max occur? Because that's really what we want to know. In some sense, this could happen to you if you set up a new aquarium and you get a bunch of fish in it. Let's say you do have the microbes required to convert ammonia into nitrite and then to nitrate. Maybe that process is happening, but you don't have enough oxygen, high enough rate of reaeration. Well, it might actually be a couple days later, after you've added all of this waste, the fish are making the waste and stuff, it might actually be a couple days before the oxygen reaches a minimum and then starts climbing back. And that's another reason why an early setup of an aquarium might be catastrophic for your aquarium fish, because you might end up overfeeding early on. For those of you interested in keeping an aquarium, I've only done really kind of simple cases, and I almost always use local fish that I catch. So I usually am working with more hardy fish and don't have to be too careful. But one thing to keep in mind is fish really can survive very, very well without being fed very often. So if you want a healthy fish, keep it somewhat hungry. It's not going to grow as big as fast. If you wanted to grow up big and fast, you feed it a lot. For any of you who've done any amount of fishing, let's say for bass, if you catch a large bass, chances are it's actually it's not that it has lived a very long time. It's more so that it has eaten a lot in the first few years of its life. So you can have a very old fish that's not very big just because it hasn't eaten much in its life. And it's that rate of consumption that gets you the very large fish. Anyway, we're talking about when the deficit happens at its max. So for that, we need a different equation. And now the fish is in the way. What we're looking at for understanding when the deficit reaches its max, we're looking for some distance. And we'll say that's x for x at C, which C is the critical point. That critical point where our dissolved oxygen reached its minimum. And that's the critical point that we're talking about. So that's what we want, that xc. We're going to relate that to the stream speed in order to get the x, that distance, based on how much time has elapsed. So the time at the critical point time, we can relate that to the distance downstream, and then we know, if we know the speed, then we know the distance, right? Assuming it's plug flow like. We just multiply to get the x, we multiply the speed times the time, or to get the time, we divide the distance by the speed, right? So it's just basic velocity conversions there. However, we have this final equation here to get us the time, and this is really just a derivation of this equation, solving for that time at the minimum deficit. So we're not going to bother with how the book got there, but you'll see some similar elements here because that's the thing. So we have 1 over Kr minus Kd times the natural log of Kr over Kd times 1 minus all of this stuff. So we've got this elaborate equation, and what we see is, again, we have these aeration, reaeration, and deoxygenation rate constants throughout the equation, the initial deficit, and the initial remaining total amount of BOD. So that ultimate BOD there. With all of that, plug in the right things and we can get our time. And again, that does assume that our KR is not equal to KD, because then you're dividing by 0. Okay, so with all of that, let's take a look at an example. Here we have example 5.6 was a previous example where we had dissolved oxygen concentration of 2 milligrams per liter and a discharge rate, and that was wastewater. So wastewater with a pretty low oxygen concentration of 2 milligrams per liter and a discharge rate of 1.1 cubic meters per second, which is actually pretty large. The river that's receiving the wastewater has a dissolved oxygen equal to 8.3 milligrams per liter, a flow rate of 8.7 cubic meters per second, temperature of 20 degrees Celsius, and we're assuming complete and instantaneous mixing. So that's important, because when we make that assumption, what we're looking at is our river, we have the wastewater added, and complete and instantaneous means right here we now can derive that L naught. There's no interfering assumptions, or the assumptions have been made, so there's nothing preventing that from being true. Because if it took a while to mix, there's some other things to consider. Okay, so assuming that, estimate the initial dissolved oxygen deficit of the mixture of the wastewater and river water just downstream of the discharge point. Okay, so I should have just kept that drawing here. So go ahead and estimate. We know something about the river, and we know something about that discharge into the river. So we'll say we've got a flow rate for the river, flow rate for the wastewater, and then we have DO for the river and DO for the wastewater. And the question is, with this mass balance here, at that juncture, what is the DO, and I'm just going to call this initial, DOI here, at that starting point. And of course here we have the mixture of Q river plus Q wastewater. Okay, so I've been drinking a lot of coffee, so I need to use the restroom. I'm going to give you a moment to look over that and solve that, and I'll come right back, and we'll pick up right here in just a minute. So I'll be right back. Okay, so if this problem got you thinking about temperature and rate constants and things like that, turns out that this is actually a very simple problem. Now, I do have something, a little table there that's kind of interesting. Um, we don't need it for the problem directly, but just so you know, there are a couple other things that affect, um, that do affect dissolved oxygen concentration. I did mention temperature, but it turns out chloride concentration also affects dissolved oxygen. So if we look at, let's say, 20 degrees Celsius, um, that might be something like 70 degrees Fahrenheit, 9 milligrams per liter if it's pretty clean water. And then if we have lots of chloride, so kind of salt, component of salt, then it drops down to 7.7 milligrams per liter. But that's like a lot of salt, though. That's 15 grams per liter. That's getting to the point where it's like almost full strength ocean water. So ocean water is going to have a little less dissolved oxygen on that basis, just simply from the chloride. Okay, anyhow, the problem is asking for us to estimate that deficit initial. I guess it would probably be better to say D with a little o. Okay, so then, well, actually, I guess we did need that table for the estimating the DO at saturation. I misspoke. So DO saturation minus DO at some point, at some time, this could be the initial dissolved oxygen. We could look at it that way. That's going to be our deficit, our initial deficit. So to know the DO saturation, we did need this textbook. We didn't really have any information about the amount of chloride. Maybe there's a fair amount in the wastewater, so maybe we have this here as our initial, but we'll just go ahead with the assumption that there's not too much. We'll just use that one. So we would say 9.09 milligrams per liter. Minus this DO of this combined river plus wastewater is going to be our answer. So let's figure out the dissolved oxygen of this mixture, and I'll go ahead and call that DO initial this way. Okay, so then we know that the dissolved oxygen is going to be in balance here because the only thing that happened was we mixed them, right? It's instantaneous, so we have complete mixing, and there's no rates happening either way because there's not enough time for anything else to happen. So we're going to say that DO times QR plus Q waste is going to be equal to DO in the waste times Q in the waste plus DO in the river times Q of the river. So just a simple mass balance, just like we've done before, based on the constituents, right? Dissolved stuff. So the initial dissolved oxygen then is going to be DO waste times Q waste plus DO river times Q of the river, all that divided by the total flow QR plus Q waste. Okay, so let me get Excel going and we'll do that calculation real quick. Okay, so what we're looking at is DO naught, and we want this to be equal to, I'm just going to go ahead and type each as we go. So the dissolved oxygen of the waste was 2, and that was times the 1.10 cubic meters per second. We're going to add this. Actually, you know what? We need a set of parentheses here. Okay, so we have that term plus the dissolved oxygen of the river, which was 8.3 milligrams per liter times 8.7 cubic meters per second in that river. All of that divided now by the total flow of the river, which was 8.7 plus the 1.1. Okay, so then our initial dissolved oxygen concentration would be 7.59 milligrams per liter. And if we check this, we have about a tenth of the water, maybe slightly more, of the water is going to be from the wastewater, which was depleted in oxygen. So we know that the combination should be less than the river had initially. The river had 8.3 milligrams per liter, and we also know that it should be, on the order of something like 10% lower, or plus or minus some. So we went from 8.3 down to 7.6. That looks good to me. That makes sense to me. So I think we're in good standing there. So then we would say this would be essentially 7.60. Well, probably just 7.6 actually. Or if we wanted 2 digits, that would be 7.59. Okay, so anyway, we have that, and now we can say 9.09 minus that is going to give us our answer. And that's assuming we have the correct amount of dissolved oxygen here. Maybe this is more correct based on the amount of chloride in the waste stream. I didn't bother going back and digging up the information provided in that previous example, but maybe there's some more context. Maybe we can define how much chloride is in here and find that, and then use the closest approximation based on this table and get a better answer. But since we're not doing that, we're gonna go with this assumption. Okay, so then that would be, so the initial deficit then is equal to the 9.09 minus that current amount. So the initial deficit is going to be 1.5 milligrams per liter of oxygen. That's the initial deficit. Okay, so that's that problem. The next problem, example 5.8, follows it, and it says, okay, just below the point where a continuous discharge of pollution mixes with a river, the BOD is 10.9 milligrams per liter. So this is a different river, different situation. And the dissolved oxygen is 7.6. The river and waste mixture has a temperature of 20 degrees Celsius, a deoxygenation constant of, so KD of 0.2 per day, an average flow speed of 0.3 meters per second, and an average depth of 3 meters. And then it tells us this is a continuation of the previous examples in terms of some of the parameters. Now, I think that this DO here, actually, that's what we just calculated, right? 7.6? Yeah, okay. I was looking at the BOD and thought that was a different number, but that must have been the previous problem. Okay, so everything is the same, actually. Average depth 3 meters. Part A says, find the time and distance downstream at which the oxygen deficit is at a maximum. And then part B says, find the minimum value of dissolved oxygen. So here what we're looking for is that, move the fish cam a little bit. What we're looking for really is the, on that dissolved oxygen sag curve for time or distance, we're looking for that critical point, right? We have something like that, and we need to know what's happening there. So we're trying to find that time and the distance, and also find out what that minimum value is. So this is a question, and this is a question for parts A and B. So we're just going to need to use the equations we used previously and the information that we have gathered so far about the system to find these answers. So we have a little less than 10 minutes. That doesn't really give us time for you to try it and then for us to solve it together. So what I'm going to say is take a few minutes, work on this problem now. I suggest you do. I'm going to end the class early, but I suggest you work on it now. We will start here next time before we get into our next lecture. And that way you'll have this chance to work on this, and we'll go through this particular problem before you have to turn in your homework. So your homework will be due a week from today. We'll go over that in class, and this will hopefully give you a chance to try it out and get some feedback along the way. Okay, so I will probably be sending an email later today or tonight with the kind of a reminder for the assignments. Again, my plan is to have your homework 3 graded and your exams graded by Tuesday next week. Okay, so with that, have a good weekend, and we'll see you next time. Thanks again for the participating in the Kahoot. I really appreciate that. All right, and of course you've got the stream up now. You can pause it if you want to work on it now, or it should be posted automatically, so you should see it there. All right, goodbye for now.